So we're getting wrapping up multiple choice momentum multiple choice 1. It is a little after midnight. I really want to stop, but I'm just really close to finishing these, and so I'm just going to punch them out. Hopefully I will make some sense as I go through this. All right. Student obtains data on the magnitude of force applied to an object as a function of time. Remember, for the area under this is going to be impulse and the change in momentum. Answer the following question for the information on and diagram above. The increase in momentum of the object between 0 and 4 seconds. Between 0 and 4 seconds. Well, it's going to be the area under here. So I would find this area first. That's 5 times 4. That's 20. Then the area of this is going to be 4 times 5, 10, 15, 20. So 4 times 20 is 80. Cut it in half because it's a triangle. It's 40. So I get a total area of 60. I would say the change is 60. I'll hand it down to the answer sheet here. 26 says it is in fact 60, yes. So there's the area under. But that includes this rectangle here and then this triangle here. Alright, 27, 31. 31. 3 objects can only move along a straight level path. The graphs below show the position D of each of the objects plotted as a function of time. Okay. Position. The magnitude of the momentum of the object is increasing in which of these cases? So we need velocity to be changing. Let's start with this. If an object stays, and this is the position, if it stays at the same position as time goes on, it's just sitting there. It's at some spot, call it 2 meters, and it's just sitting at the 2 meter spot. Just sitting there. So here, velocity is 0. So, no. I need a velocity. Okay, well this has velocity, right? Yeah, it's got a velocity. And so, is the velocity changing? Velocity is the slope of this line. So, and that would be constant. It would be delta D over delta T, and it would be the slope of this line would be the velocity, but that slope isn't changing. So the momentum isn't increasing because momentum's mass times velocity. This, the velocity is there, but it's not changing. Here there isn't even momentum. Here it has momentum, but it's not increasing. So that must mean this one. This one has a changing slope, which means the velocity is changing. It's speeding up. Velocity changes, so does the momentum. So I would guess 3 alone. B would be my answer to 31. That would be correct. 32. Force sensor cart of known mass moves with a known speed along a level frictionless track as shown in the figure above. The cart hits a sensor and rebounds. The force sensor measures the force exerted on the cart as a function of time and as a function of the position of the cart. The results will be graphed in the axes shown. Which of the following 2 graphs can be used to determine the cart's speed after it rebounds? Alright. So, I would anticipate that this force would, over time, would rise to a maximum when it's completely depressed, and then reduce, but it would still be in this direction the whole time. So I'd expect something like that. Position of the force, I would still expect the position to increase but the displacement here is interesting. The position's interesting. Where's where do you want to make the 0 point? So we could say, if the force is negative, then the displacement's negative. So let's call the force positive. Let's say this way is positive. So the force that is going to be negative. The displacement's positive. So it's going to go, interesting, it's going to go backwards and come back to here. And the force is going to increase. The question is, where's position 0? And if you call this way positive, then the force would be negative and it would be down in here. Interesting. Interesting. Let's take a look at what they ask us again. They want to know which of the graphs can be used to determine the cart's speed after it rebounds. Well, if they know the mass and they know the speed, I can give you the change in impulse right here. I can give you the impulse, which is the change in momentum, and that would be enough to do it. I'm having a hard time what this would look like, let alone how I would use it. So I would go with this, I think. Let's take a look, see what they say. Maybe this will be the first time I get one wrong. I would say graph 1. Not by that. So if you knew the force times distance, you might be able to use both of them. Maybe I would say I'm either going with A or C right now. Because I'm struggling with what this might look like and how the negatives and positives would work, I'm bailing out on it. But that just could be I'm not fighting it hard enough to find out. It is almost 12:20 at night. They say, let's take a look. 32. 32 says C, so you could do it with either one. So my issue is, certainly I could do it here. Would make sense here, if I know the mass, I know the velocity, and I know the work done, right? Force times distance. Get the positives and negatives right, which are apparently what's bothering me, but I still can measure a force and the distance it moves, then that would be change in kinetic energy, so I could find the final kinetic energy. So yeah, I mean, regardless of what I guess this graph looks like, the area under it is the work done. And the work done is the change in kinetic energy. So, yeah, okay. I don't have to even know what the graph looks like. I just have to know what it's used for. So I'll go with C. Fair enough. A semi-mistake, we'll call it. All right, 35. Two particles collide and stick together. If no external forces act on the two particles, which of the following is correct for the change in total momentum and the change in total kinetic energy? Okay, so you haven't run across this yet in lectures and so forth. It comes down to two types of collisions, well, at either end. So one type is the kind we have here. Two objects come together and they stick together and form one object. Two train cars that hit and latch together, for example. Two lumps of clay or something. There's a bunch of different ways. When that happens, so when the objects stick together, then that is a inelastic collision. If objects bounce off each other, so they come in and they bounce perfectly off of each other, so they come in one way with velocities like this, but they leave the opposite direction, just bounce right off, those are called elastic collisions. Here's the deal. Momentum is conserved in either one. So momentum's conserved. If it's elastic, then you can say the kinetic energy initially is equal to the kinetic energy final, but only if it's perfectly elastic. If there's any kind of deformation, then it's not going to be the case. So two particles stick together. If no external forces act on the particles, which of the following is correct changes? So the momentum should not change for the system. But the total kinetic energy is going to change, and it's going to drop. So two particles collide and stick together. I don't know if we know. We don't know if the two particles hit and stop. So I would just say the change in momentum is 0. First of all, it's one of those. The change in kinetic energy is negative. It's less than 0. This means it doesn't change. This means it increases. It doesn't increase. It's got to go down. So C would be the right answer for 35. Yes. All right. All right. 39. Last one. There we go. A ball is dropped and bounces off the floor. Its speed is the same immediately before and immediately after the collision. What's true about the collision between the ball and the floor? Well, the ball's momentum changes direction, but not magnitude. I will buy that, because it has the same speed, but the direction's completely changed. So I would buy that. The ball's momentum is not conserved. It is not the same before and after. It has a negative momentum before, for example, and a positive afterwards. That's because the Earth's force, in that case, would be the floor's force has been external force. The ball's momentum changes magnitude, but not direction. No, it definitely changes direction. The impulse delivered to the ball by the floor is 0. Nope. It is double. Remember, it's not yet. It's going to be double that change. The impulse delivered to the floor by the ball is 0. And that's technically got to be 0 wrong as well. Technically speaking, it's got to be the same impulse on either one. You just wouldn't notice it when you're moving the building. So the best answer is the ball's momentum changes direction, but not magnitude, because the speed is the same out as it was in. All right.